Yes, we see your pointer, but not a laser pointer.
Then pointer options. Okay, that is hopefully a little bit better. Okay, good. Then welcome to my lecture today. Thank you for the kind introduction. Besides being in the Laboratory of Physical Chemistry, I'm also heading the Center for Multiscale Electron Microscopy of Eindhoven University. And TU Eindhoven is involved in NEMI as the flagship node for cryo, in situ, and ultra-fast electron microscopy, and mainly related to soft matter systems. Now, since over the last months, many of the PhDs and postdocs from TU Eindhoven have already presented their work in detail. I decided to give a little bit more of an overview, and as you can already see from the title, I would like to take it a little bit from the light side, looking at two different perspectives of what EM can contribute to the field of material science. Now, this quote actually came in discussions with a colleague of mine, looking at image analysis problems and trying to find the commonality in all of these problems, which is this talk also today about. Now, I would like to first start with where I have been initiated into electron microscopy. That would be exactly here, and I'm really not joking. This is the Triebenberg Laboratory for High-Resolution Electron Microscopy and Holography. So situated indeed in a very, very beautiful place and away from all users of electricity. As we know, electric and magnetic stray fields significantly affect, of course, the performance of electron microscopes. That is quite an extraordinary building, which is in two parts. The left part is for all equipment part, like for instance, air conditioning system. And the right part is for 6 microscope units, each house-in-house technology with a separate foundation for the microscope and a separate foundation for the operator. So ideal conditions for electron microscopy. And this is an art which we can unfortunately not find in too many universities. Now, very early on in my education, I have been exposed to the following saying, and I guess most of you know that from Richard Feynman: just see where the atoms are and you can analyze any chemical substance. Now, in this process, my teacher, Hannes Lichte, always reminded me that is not quite complete, because there's important extension and which fields surround them. Because looking from a chemistry perspective, we all understand this bonding, which is basically the electric fields between atoms, are as important as where the atoms are. And this actually education has also shaped quite a bit of how I'm looking at electron microscopy. Now, and still, we have run quite far with a hypothesis that is about 100 years old by now, that electrons actually have wave-like properties, in that we can use them in an electron microscope to image very, very small things. And it still puzzles me today that electrons can have wave and particle-like properties at once. We have all gotten rather used to it. For instance, we know that 100 keV electrons have a certain wavelength of about 3.9 picometer. And if we go to 300 keV, is about half of that. So how does it come that electrons are waves? Well, let me start here with what I guess every one of us had in his education: wave interference, with the beautiful example of the Thomas-Young double-slit experiment. So as you can see here, by having sunlight passing through an first aperture, we're creating a radially symmetric wave, which, when it then transmits through a double slit, creates this beautiful interference pattern, composed of bright stripes where we have constructive interference and dark fringes of destructive interference. Now, I think we're all very familiar with that, but I would say fewest of us actually have seen that these experiments also have been carried out with electrons. And here I would like to go back to some very, very early experiments carried out by Klaus Jönsson and Mölnstedt, or Mölnstedt and Büker, on the interference of electron waves. Now, on the top, you see the slit image. Here, in this case, a single slit, on the right side, a double slit, and on the bottom, you see the interference pattern. Of course, in this case, we're not reproducing ideal image of the slit, as this slit is not in a plane, in an image plane, so we get, of course, Fresnel fringes. But what we can see already in these very beautiful experiments is that the double slit experiment also works beautifully for electrons. But there is one difference in interpretation when comparing now light waves and electron waves. It is that electron waves are actually probability waves, so that bright fringes correspond to many electrons hitting the screen at this given point, and for destructive interference, actually no electrons hitting the wave. So now, having established that electron waves have amplitude and phase, let's look at this a little bit more in detail. Now, when thinking about the thickness of a TEM sample, being for high resolution only a few tens of nanometers thick, and looking at the velocity of the electron, let's say for 300 keV is about 3/4 of light velocity, it is quite clear that there will be relatively little amplitude contrast or absorption of the electron wave in that material. So that brings us actually to the conclusion that phase must play a significant role in electron microscopy. And that this is indeed the case, because most information is actually encoded in the phase, as TEM samples are phase-shifting objects. Now, in a very similar analogy as to light moving slower through glass, we can see here that an electron wave, a plane electron wave that is interacting with a specimen, will just have its wavefront bent due to the presence of the electron. So plane electron wave is bent by the sample's electromagnetic potential. In a little bit more quantitative form, the phase shift that we can locally observe on our sample is related to an interaction factor. And now the path integral of the electron through the sample summed up over the observed mean in the potential. But this is actually only the first part of interaction. There is a second part to it. And this is on account of the Aharonov-Bohm effect, that electrons experience a phase shift due to the enclosed magnetic flux. And that allows us with much accuracy to analyze this information if we would be able to do an interference experiment. But what we conventionally do in transmission electron microscopy is displayed here. Now, this is a simple scheme that looks at an electron microscope in terms of simple Fourier optics, just looking at the object plane, shown here on top, and the image plane. And now what is called contrast mixing between the object exit wave in terms of amplitude and phase occurs due to the contrast transfer function, which is of course given by the defocus as well as the aberrations of the objective lens. So what now happens is that in the back image plane, the amplitude and phase of the object exit wave get scrambled so that we have contributions from both of them. And conventionally, the amplitude is now recorded on our CCD camera in an intensity image. And to now optimize our phase contrast for the object structure of interest, we're trying to tune our phase contrast transfer function, so shifting information from the phase of the object exit wave into the amplitude of the back image wave onto the intensity in the CCD camera. So that phase channel that you see here on the right is conventionally blocked, especially when looking at just standard bright field TM imaging. But since we know that the phase actually contains most of the useful information about the sample, it is, of course, very important of how to retrieve these phases, and there are a number of ways. So with that, I would just say phase retrieval is actually an essential problem in any type of electron microscopy, be it transmission or scanning transmission, and a number of different approaches exist there. That would be, for instance, focal series reconstruction, also termed inline holography. Now, more recently, integrated differential phase contrast would be a technique, or for STEM approaches, tachography. What I will be briefly looking at in the following slides is actually how this can be done by a technique called off-axis electron holography. On the left side, you see the schematic beam path in the objective lens to the back image plane. So in electron holography, we're actually doing an interference experiment that overlaps the red and the blue part of the electron wave that is on the left and the right side of the optical axis. Now, without a sample being present, part of the wave transmits on the left, transmits on the right, crosses in the back focal plane, and then gets to the region where the biprism is located. Now, by applying a positive voltage to this electron biprism, which is conventionally just a thin glass wire that is coated with a conductive material such as gold or platinum iridium, we can deflect electrons that pass on the left to the right and electrons that pass on the right to the left, so that we create now an interference pattern between the left and the right side of the objective, left and right side of the biprism. Now, to show you how that actually works, I have a little movie here. What you see here is in conventional operation without the voltage being applied to the electron biprism, just the shadow of the biprism. And since this is significantly out of focus, you will also understand that we see here significant Fresnel fringes on the left and the right of the biprism. Now, by slowly ramping up the voltage on the biprism, we first remove the shadow. And if we continue, we're creating an interference pattern whose fringe spacing and overlap width are actually adjustable by the voltage. This was now briefly a higher resolution image of the interference pattern that would be created here in the center. And now to do a proper interference experiment with an object actually present, the object is only inserted into one part of the beam, for instance here on the right, so that we have an interference of the object exit wave transmitted through the sample and a reference beam. And that will then conventionally result in images like this. So we very nicely see interference pattern just without any distortions, where we have just transmitted vacuum. This is a magnetite crystal of about 50 nanometers in length. And this is part of the carbon film on which edge the magnetite crystal sits. What you can immediately notice is that if you're following one of these fringes, is that you see that the fringes are bent as well as they change in contrast. And this is actually how in electron holography, off-axis electron holography, the information about the amplitude is encoded in the, let's say, brightness of the fringe when you follow it. And the phase is encoded in the bending of the fringe with respect to its position in vacuum. So we're really recording amplitude and phase in one go in an interference pattern. Now, since we have recorded the information, we also would like to, of course, retrieve it. And for that, we need to do the following. So we're taking our electron hologram, we Fourier transform it. That would be the Fourier transform of that particular hologram, for instance. And now we're selecting what is termed a sideband, which contains the information of amplitude and phase. And by inverse Fourier transform of this just cut out region, we can retrieve the amplitude image as well as the phase image of an electron wave interacting with a magnetite crystal sitting at the edge of a carbon film. Now, magnetite, I guess most of you will know, is magnetic. So in this case, the phase image does not only contain information about the mean and the potential, but also of the magnetization. And now, by acquiring two holograms with opposite magnetization direction, I can actually isolate from these phase images the contribution from the mean inner potential as well as the contribution from the magnetization. And if I'm taking now a line scan and just plot the phase shift that is measured along a pixel position in the image, I can see, okay, this material has a nice peak at the position of the magnetite crystal corresponding to about 5 or 6 radian phase shift. And we have a phase shift resulting from the magnetization, which is a much, much weaker signal, probably here in this case by a factor of about 10. And this really gives us quantitative information on what we're looking at. But again, in this case, we again have the projection problem in electron microscopy. Either we know the thickness of the material, and then we can determine what the mean inner potential or the material is, in this case magnetite, or we assume that we have a given material, and then we can, from the phase shift, accurately determine the thickness at every position of the magnetite crystal, for instance. Now that, of course, is a little bit of a problem. What we actually often would like to do, and this also in the spirit of really quantitatively using the electron microscope to measure materials properties, we can go about it with electron tomography. And that indeed can be done. Electron holographic tomography exists. Let me try. Okay, that would have been a series of phase images acquired from 7 magnetite crystals, acquired over a tilt range of plus minus 66 degrees, 2-degree increments. And from this now, with the standard sequential iterative reconstruction technique with 30 iterations, the 3-dimensional information about this, let's say, nanoparticle assembly can be obtained. And the beautiful thing about holographic tomography is, since the phase signal, so the input signal that we're giving to the reconstruction algorithm, is quantitative, we can actually determine now in every voxel of this reconstruction the measured mean inner potential. So now we have resolved the problem of projection, and we can actually measure in every point which materials property we have. Now here I'm just showing what a histogram of this reconstruction looks like. We have a little peak at vacuum level, and we have a peak that is at magnetite level, and that is very close to the actually predicted mean inner potential in magnetite being 17 electron volts. You can see from the reference that is work from a very, very long time ago. And at that time, this technique was unfortunately not automated. So acquiring all the holograms with reverse magnetization and so on was 12 hours straight on the microscope, which I cannot recommend. But just getting, for the first time, these type of results is actually quite exciting. Now, by now, electron holographic tomography has been automated to some extent. It's one of the last techniques actually that has. creating interference patterns also with reference holograms. These 2D holograms will then have all to be reconstructed, meaning isolating the amplitude and phase information, and then they can be aligned and used using a back projection or other means to create a three-dimensional map, three-dimensional mean and a potential map of a structure. Now, what would that be useful for? Well, one good example is actually shown here. This is a part of a PN junction prepared in a, let's say, cylindrical shape. And now when measuring across the PN junction, we can clearly see now from the n-dope region being about 15 electron volts in mean and a potential to the P region being slightly below that, and this being a very clear proof of how these systems or how doping in this PN region actually affects the electric properties of the material and enables many, many things in semiconductor industry. Now, this is a very particular view on electron microscopy, trying to push techniques forward to quantify to the best of our abilities the structures that we're seeing. And I think this is a very, very important part of electron microscopy technique development. But if it's about actually looking at the shape of structures only, then, well, we have actually many, many more possibilities open. And here, a quote from another one of my heroes, it's not nature in itself that we are observing, but which mode of microscopy or imaging we're actually using. Now, staying with the topic of, let's say, three-dimensional imaging, which I have been heavily involved with over my career, then transmission electron microscopy, there's quite a number of different techniques that are possible, and each one of those will give you a different result in terms of the information that you're obtaining for it. Bright field being rather difficult to quantify in terms of CTF filtering, of course. Energy filter TEM, much better possibilities, but again, also a very high dose technique that is very difficult to apply to beam sensitive materials. And in a dark field and weak dark field, rather difficult to quantify. Electron holography is really one of the best techniques to really get quantitative information of the material at hand, probably together with high angle and in the dark field, where we have a C-square dependence of intensities. And then, of course, for atomic resolution, diffraction tomography, also high angle and in the dark field, and then the entire side of scanning TM. So that gives us, of course, a broad range of techniques to look at it. And that brings me to the second part. Now, very often in our material science questions, it's not really about the very fundamental properties, such as mean and a potential over a PN junction that we're looking at, but we're studying more the morphology or the shapes of the assemblies that we're looking at. And in this case, a beautiful example, binary nanocrystal superlattices, beautiful publication, and we see just dots of different brightness or darkness, so as to say, which nanoparticles can assemble in a very, very broad range of morphologies. There are some atomic equivalents, such as sodium chloride, copper gold, or orthorhombic AB, but also in these systems where structures have been found for which there is no atomic equivalent. And to resolve these, let's say, supralattices, I would ask the question, would it actually be needed that we are able to identify by microscopy methods if we have here a gold particle or there a lead selenide or other materials? And the answer is actually no. So this is actually my hookup. Does then matter actually really matter? And for these shape analysis or morphological studies, I would argue there is very little need in terms of quantification of contrast, as long as we see contrast differences between the parts that we want to distinguish. But what does matter? And in this case, indeed, interactions and shape matter, in particularly when we want to look at the analysis of these rather complicated systems. Now here, an example, for instance, if you go down from the nanoparticle level to the level of ions or small molecules, there's actually a very, very different scaling of the different parts of interactions in these systems. For instance, dispersive and Coulomb would be on the nanoparticle level very far up, but are very separated if you go to the level of ions or small molecules. So that means when looking at these materials, length scales truly matter. For analysis, as I said, time being a component also is a very, very relevant, particularly if you're looking at the life cycle of materials. And in the end, shape or morphology indeed matters because it can make an analysis very, very easy or very, very difficult. So in the following slides, I will look a little bit more at the role of shape or symmetry in the analysis of transmission electron micrographs and more specifically obtained by tomography. The first nice example, of course, simplest symmetry would be spherical. And these superlattices can be prepared, as shown from the earlier paper, via the evaporation of the solvent, so increase of concentration and assembly of the superlattice at the liquid, in this case, air or solvent atmosphere, and they can be deposited then as a floating layer on top of a TM grid that is just submerged in the liquid. Even though the projection requirement is not fulfilled for these type of materials, you can see significant effects of crystals going in and out of diffraction conditions. Since this only happens for a few images of the entire tilt series, the quality of the reconstruction is not significantly hampered. So that still allows analysis of now this rather large assembly and just going through this slice by slice from the carbon film to the top and back just provides actually a wealth of information of these really truly beautiful assemblies. And we can already see that there is different crystalline grains that occur during this assembly. One largest crystalline grain is shown here, and that has also been analyzed in somewhat more detail. So for spherical symmetry, how to go about it? Well, since it is very simple, we can use templates. Templates of a sphere are easy to create. We only have to take care of translation when matching them or via cross-correlation in the different parts of the reconstruction. But since we are in this case working with nanoparticles which have varying sizes, we also need to vary the template size to really detect all of them. So from this cross-correlation, we can then determine the centers of each of these nanoparticles, and from a radially averaged intensity profile, by just setting at half the intensity between the inside and the outside of the nanoparticle, we can very accurately determine also its radius. Now, this is very, very useful information to look now at the ordering in these materials. So analysis to get to X, Y, Z, and R coordinates is very simple. Now, the more difficult part is now building together there which actually lattice is formed. That, of course, can be done by visual assessment, but also in somewhat more complicated ways, for instance, using local bond order parameters, which was used in this case. And then we can see that the unit cell of these assemblies, here being atomic equivalent being aluminum diboride, or an ICO 8013 structure, can be nicely extracted. Furthermore, of course, this is not only a technique that applies to binary nanoparticle superlattices, but of course can be extended to any type of these superlattices formed from nanoparticles. So basically the detection of X, Y, Z, and R will be all the same. Here an example of a ternary nanoparticle superlattices that we very luckily found. So it's an aluminum magnesium tetraboride structure, and that was very surprised that we found this. It seemed that it had been epitaxially grown on an aluminum diboride structure. So in this case, you see here in the bottom, it's an AC2 structure, and on top of that, you see the formation of this ternary superlattice. So with these very, very simple techniques, actually a very broad range of these very exciting and fascinating materials can be simply analyzed due to just having spherical symmetry. But there are also many other systems that have spherical symmetry and where similar procedures can indeed be used. Another example of this is polymer vesicle formation, and this has been done in the liquid phase. The series of liquid phase TM images was in this case manually aligned because at such low contrast and such varying structures, that seemed to be also the best way forward. And below the individual snapshots of the movie, we see some time averages which clearly show the transition from what seems to be a more solid sphere into a polymer vesicle. And I'm also very happy that Hang Long, who has been really putting a lot of the heavy work in there, is also present today. Now, where does radial averaging come in? Radial averaging comes in when we want to look at the evolution of contrast. And of course, just for instance, taking a line scan across the center now of this particle will give us quite some interesting information. For instance, how does the contrast of the vesicle wall evolve? But again, it is something that is local to the right or the left side of the formed vesicle. I think a more comprehensive view of how this happens across the entire surface, which of course is a mobile structure, comes when we're doing now radial averaging, looking at intensity evolution in dependence of radius and time. And this is shown here. We see that at the beginning, we indeed have more spherical-like structures. So there's just a little bit of contrast with respect to the surrounding liquid. And there seems to be a slight growth, but then from very early on, the size of this vesicle stays constant, and only the contrast within that wall is evolving and basically becoming densified. And this can be explained that in this case, we have now a sphere, a polymer enriched phase that contains still organic solvent molecules, and that with the expulsion of these organic solvent molecules, the inside becomes more aqueous and the wall becomes more defined or denser packed as solvent molecules are removed. Another example of where spherical symmetry was rather useful in the analysis are these supraparticles, which by themselves can be organized into larger structures. So we have polystyrene spheres and silica particles at the corresponding pH due to surface functionalization one will have a positive charge, a positive surface potential, zeta potential, and a negative one, and that gives an electrostatic interaction that results in the assembly of supraparticles. Now, upon further increase in concentration, then additional assembly steps will take place. And what can be nicely analyzed, also again being based on the spherical symmetry, is now the coverage of silica particles on these polystyrene spheres. And for instance, if we have a certain radius of the supracolloid, only a certain number of silica spheres will fit on the surface, so having a distribution of 4, 5, 6, and 7 neighborhoods. The moment that we're getting somewhat larger with the total size of the supracolloids by adjusting the size of the internal polystyrene spheres, then we're only observing that 5, 6, or 7 coordinated environments are allowed. And upon increasing the concentration of these supracolloids in solution, even large ordered structures can be formed, as shown here by FIBSEM tomography. And this, to our knowledge, is indeed the first case that we have an assembly process of a multi-scale material that is structured on more than one length scale that combines an enthalpy-driven, so this first step, and an entropy-driven process. Now going away, radial symmetry would yet now be the next important or next difficult structure. In this case, we looked at carbon nanotubes and their assembly in 3D, depending on the aspect ratio of the carbon nanotubes. In this case, analysis, position, diameter can also be obtained by cross-correlation with templates. In this, we use templates which are tube-like. Again, we need to account for dispersity in the system, so varying size. And here, complexity results by having different orientations of these tube segments. But with this approach, each of the carbon nanotubes could be detected in this compact, just showing here. And now from this information of packing, we can derive even additional information. For instance, by using a simple criterion, such as that if the distance between tubes crossing is smaller than the sum of their corresponding diameters, then we have formed contact. And that even allows us to estimate the contact size. And this relates very, very much to the properties that are observed in this material, which is, of course, an electrically conductive material, such that we can now describe packing, connectivity in the system, as well as conductivity in the system quantitatively, just from analyzing the morphology of the material. Now, another example where radial symmetry plays a role would be, for instance, now a very different type of material, ordered mesoporous silica, SBA15. This material is assumed to be consisting of straight channels that are hexagonally closed packed. I do agree with the hexagonally closed packing, of course, but straight channels is not what we're seeing in electron tomography. So that requires then an analysis that takes this into account. So by looking at each individual slice of the reconstruction and then perpendicular to the pore direction, we can make a model of the material that involves either having the pore with a random center or with a random diameter. random diameter shown here, random center shown here. And by combining these two, we can really measure very accurately how pore diameter, and average deviation are correlated along the entire pore length and between pores. And in this case, again, radial symmetry is quite essential to enable all of these analysis methods. Now, something that we're now going to more recently, that would be bilateral symmetry, or looking at plates, for instance, graphene networks, which we would like to structure then in stretchable conductors. Here an example of how that looks using in situ SEM. So basically exposing the material to a strain inside. In this case, it's up to about 50%, and observing crack formation in this network structure. So problems that could be addressed with this graphene and other 2D materials are, of course, very functional materials beyond electrical conductivity, and they may be in the future assembled into devices using solution techniques. Particularly interesting in this case is indeed when different types of materials are stacked on top of each other. That would then be referred to as van der Waals heterostructure, for which already a number of emergent properties have been reported. Now, going beyond bilateral symmetry, let's look at something that is really asymmetric, so really a unique three-dimensional structure. In this case, I'm going back to liquid phase electron microscopy. Experimental protocol here, it's basically the precipitation of cobalt with carbonate ions, which can be stimulated by just depositing two chemicals on the two different chips, closing it up, and then the reaction starts. Of course, there is a delay when we start observation with respect to the start of the reaction, but that is not a problem to look at the process or process dynamics quantitatively. Now, we know that we have amorphous cobalt carbonate formed, so that gives us a bit of an interpretation. And here, the images both recording bright field as well as high angle annular dark field stem at the same time, and that also at different doses. So for the analysis of these, let's say, unique or asymmetric structures, let's first try to establish what are we actually looking at. And there we have to look at the edge of the illuminated area, because of course the electron beam causes radiolysis in the liquid and results also in the deposition of a homogeneous layer of cobalt carbonate within the viewing area, which is not observed if you're looking outside. It's much, much brighter here. As you've seen, these structures are growing in time, and now it is interesting to look at how this growth trajectory works. So the model that we're having now, we have a cross-section of the liquid cell. We see particles that are growing in time, as well as deposit in the background that we need to take into account. However, that only occurs within the illuminated area. So to separate the two things, we have a background signal that is, of course, varying in time, and we also have a particle that is varying in time. If we're now adapting this mask, the mask obtained for bright field, since this has a higher signal-to-noise ratio, we can really look quantitatively at the H8 stem signal, just cutting out the corresponding region, and we can do exactly the same. In the left side, we have particle, deposit, solution, plus the signal from silicon nitride. On the right side, we have deposit, the solution, plus the silicon nitride. So we have actually, if we subtract the two from each other, all that is left is basically what's happening in the particle. And here we can use that the HA stem intensity is actually a function of the thickness and the thickness of the particle. And if we're now taking also the XY growth into account, we can really look at volume evolution in the system just from two-dimensional images. So the sum of intensities now that we're measuring over this mass is basically proportional to the volume in time. And just to show you this, that looks roughly like that. And if we're now looking at this volume increase, depending on the electron dose rate that is applied during imaging, we see differences. So it seems the electron dose rate is actually driving the assembly process, and let's say deposition of the cobalt carbonate goes in a linear fashion. Now, in view of time, I'm not going to go into detail because it is very surprising why this is linear actually. But let's focus on that we would like to obtain actually what is happening in the solution in the vial that we have in our chemical lab. And that can now, in this case, be obtained by extrapolation of the effects from the dose to zero electron dose. And we could indeed prove that this volume growth rate is exactly the volume growth rate that is observable in the vial, because we looked at regions that have not been illuminated during the experiment, and this is exactly where we observed this volume growth rate. And now, summing up all of this information, we could actually establish the mechanism by which this material grows, and also what is the effect of the electrons that we're depositing in the system and how it is driving actually the conversion into cobalt carbonate. Now, close to the end, a few more brief notes. Asymmetry in 3D. Well, this is a spherical particle, so not asymmetric, but it's structured asymmetrically on the pore level. Now, also extending electron tomography to very thick samples. This was a porous silica sphere of 2 micrometer in diameter. And for this case, we could reconstruct this entire micrometer-sized porous silica sphere and then measure independently along the X, Y, and Z axis of how average pore diameter and strut size distribution is distributed throughout that, let's say, multi-scale material. And to our surprise, indeed, there are variations. It seems that porosity on the surface of these particles is somewhat higher, definitely the mean pore diameter, than in the center. And that is related to actually the formation of these materials in during emulsion templating, where we see a collapse, but that was observed by in situ optical microscopy, and I think was a little bit outside of the topic. Now, what can we do with this? We can also use this now to directly simulate diffusion in these systems. These are silica or silica spheres that are used for high performance liquid phase chromatography. So they're actually quite essential for purification of macromolecules. Now, with that, why would all this matter, what I have just said? Well, and this is where I like to take a little bit more the position of a material scientist or a materials chemist. Now, I think many of us work on problems that in one way or another involve self-assembly or the creation of materials. So of course, a big question is of how far can we push chemical self-assembly? And I do believe that linking the scales from the nanometer to the micrometer is electron microscopy is a very helpful tool. But I still do believe that things like, for instance, a mobile phone will for a very long time not be able to be assembled via self-assembly alone. So what is the next step then there? Well, then the question for me comes, how can we now combine bottom-up and top-down approaches? For instance, self-assembly on the smallest length scale with, for instance, 3D printing on the larger. And this is also things that we're working on in the group. And the last question, how far can we optimize properties and performance by morphology alone? Because we have problems in our society. And in many cases, we would like to get to sustainable or let's say non-polluting materials. and still get the same performance out of these materials. So the question then comes, can we now find a replacement with a suitable morphology that can do exactly the same job? And for that, we really need to connect the length scales. So from the atomic or colloidal level via first stage of assembly into superstructures, via additional, for instance, top-down templating techniques, such emulsion templating, to even 3D printing, to create really the hierarchical morphologies that I think will be able to solve our societal problems related to many things in energy, food, or health. With that, let me summarize. Does matter matter? No, morphology, I think, seems rather important. Symmetry of building blocks are quite important for the type of analysis that we can do. From 0D being reasonably easy, 1D possible, 2D is a bit more tricky, but should be possible, and fully 3D rather difficult. But there we can now tap again into what I have presented in the first part of my lecture, linking actually quantification, quantitative information, looking at compositional heterogeneity, and combining that with indeed three-dimensional information. And as I noted on the last slide, that's not the only answer. Yes, matter matters, particularly when we look in terms of a material's life cycle, in terms of sustainability, in terms of pollution. And with that, I would like to thank all my colleagues, students, PhDs, postdocs, collaborators that have joined in this journey, everyone that has been specifically acknowledged also on the slides. Very, very big thanks. And I would like to thank you for your attention.